this video, I just want to do another optimization problem, and the problem we have today is a cylindrical can is to hold 20 pi meters cubed. The material for the top and bottom costs $10 per meter squared, and the material for the sides costs $8 per meter squared. Find the dimensions of the can that is most economical. So we need to find the height and radius of a cylinder that will give us the least amount of cost. So I would start off by drawing a picture so we can visualize this. So we have a cylinder with the radius r and height h. So now we can write our equations, and remember there's two. There's the constraint equation and the optimization equation. The constraint equation I like to call the known equation, and the optimization equation I like to call the unknown equation. So in this case, the known equation would be the volume equation, since they gave us the volume of the cylinder is 2 pi meters cubed. So we can set 2 pi equal to the volume of the cylinder, and remember the equation for the volume of a cylinder is pi r squared h, so 2 pi equals pi r squared h. So that is our known equation. And our unknown equation would be the cost equation, since that's what we want to optimize. So we need to write an equation for the cost. So the cost of the cylinder would be each of the prices times the area of the corresponding part, right? So we have $10 for the top, or the circle on top. So it's $10 times the area, right? Because it's per meter squared, so that's the area of the circle on top. So $10 times, the area of the circle is pi r squared, so it's 10 times pi r squared. And we have another one of those, since it is a bottom up piece, so we can change this to 20, since we're adding two of them. Plus, we need to find the area of the thing in the middle, multiplied by the cost of 8. The thing in the middle is, again, 2 pi r h, so we need to multiply that by 8. So that gives us 16 times pi r h, right? Because 8 times 2 is 16. So 8 times 2 pi r h will give us 16 pi r h. So that is our unknown equation. So now, notice that we want to take the derivative of the cost and set that equal to 0, so we can find our r that would give us the minimum value. But we can't take the derivative of the cost because we have two variables on the right side of the cost equation. We have the radius and we have the height. So we need to get rid of one of these variables so we can actually differentiate the cost. And notice that it's best to get rid of the h, and to do that we can solve for the h in the known equation and substitute that value into the unknown equation, and then we can differentiate after that. So let us solve for the h in the known equation. So we get h equals 20 pi over pi r squared. The pi's will cancel out, so we get h to be equal to 20 over r squared. So now we can substitute this in for the h there. So we can rewrite our unknown equation as c equals 20 pi r squared plus 16 pi r 20 over r squared. The r's cancel out. This becomes a 1, r to the first power. So we can rewrite this as 20 pi r squared plus 20 times 16 is 320 plus 320 pi over r. So we found our new cost equation to be 20 pi r squared plus 320 pi over r. So from the previous step, we got the cost equation. So now what we need to do is we need to take the derivative of this cost equation and set it equal to 0. So we can find our r value that would give us the minimum cost. So in this case, we need to find c prime. So I'm going to rewrite this as 20 pi r squared plus 320 pi r to the negative first power, so we can use the power rule. So the derivative of this would bring down to 2, so that would give us 40 pi r plus, bring down the negative 1, negative 320 pi r to the negative second power, right? We're subtracting 1 from the exponent. So now, if we simplify this, we get 40 pi r minus 320 pi over r squared. And I'm going to make this into a single base because it'll be easier to manage in the future. So I'm going to multiply this by r squared over r squared. So this equals 40 pi r times r squared over r squared minus 320 pi over r squared. This would give us 40 pi r cubed minus 320 pi all over r squared. So again, we got our C prime value as 40 pi r cubed minus 320 pi over r squared. And remember, we need to set this equal to 0 so we can use our first derivative test to actually find a value for r that would give us the most economical dimension. So what we need to do is, again, we need to set this equal to 0, and notice that the only way that this function equals 0 is if the numerator equals 0. So let us set the numerator equal to 0. So we get 40 pi r cubed minus 320 pi equals 0. 40 pi r cubed equals 320 pi. Knock out the pi's. 40 r cubed equals 320 divided by 40 r cubed equals 8, and then r equals the cube root of 8 is 2. So in this case, we've got the radius to be 2 meters, but we can't just state that the radius of 2 meters would give us the most economical so we actually have to prove that, and we can do that by using the number line test. So let us do the number line test, and let us keep 2 over here, and remember we have to test points into the derivative function. So let's take a point less than 2 but greater than 0, like let's pick 1. Notice if you pick 1, this numerator will be negative and the denominator will be positive, so we would get a negative value. So negative value down sloping line, and if you pick a number greater than 2, like 5, the numerator will be a much larger value, and so it would be a positive number. And the denominator will also be positive, so positive over positive is positive, so we would get a positive value for a number greater than 2 if we plug it into the derivative. Notice that this makes a U-shaped or like a V-shape, so this is indeed, 2 is indeed a minimum. So we figured out that at r equals 2 meters, the can has the least cost, but we're not done yet because we need to find the other dimension, we need to find h. And if you remember, we can use the volume equation because they give us that the volume is 20 pi meters cubed. So we can say that 20 pi equals the volume of the cylinder, which is, if you remember, it's pi r squared h. We know r is 2, so we can say 20 pi equals pi times 4 times h. We can divide by pi, so we get 20 equals 4h, and h equals 5. So at the radius of 2 meters and with the height of 5 meters, we will get a can that is the least cost. And again, we proved that at 2 meters that is the minimum by using the number line test, and we noticed that this is a V. So anytime when you do the number line test and a point it has a V, it is a minimum, and in this case we do because we have negative and a positive. Thank you guys for watching, and please comment and subscribe below.